Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. We're continuing down the path of the interstellar medium and the stuff between the stars and the Milky Way. And so we're looking at giant molecular clouds, and these are enormous, enormous regions out of which stars form. And so what we're looking at in the background is European Southern Observatory's view of the Lagoon Nebula, an extraordinarily high definition view. And I'm kind of highlighting with the word the edges of the Lagoon Nebula, which branch out into darkness. But that darkness actually belies a huge number of a huge amount of cloudiness in the background that's not being illuminated by the baby stars. So these giant molecular clouds are actually the places where star formation is occurring in the densest regions. And so these are the homes of stars. So let's go back and look at the nature of what the sun is. When we talked about the sun, we found that it was about 4.5 billion years old. That's how old it is. That's how long it's lived. It's got another 5.5 billion years left before it's dead. But we find that today it's in hydrostatic equilibrium, meaning gravity and pressure are in balance. Meaning if you push on a little bit, the interior pressure goes up because it gets hotter and it pushes it back out. Or if it's pushed out too much, gravity says, no, you went too far, and pulls it back together. That's hydrostatic equilibrium. It's also in thermal equilibrium right now because there's an amount of energy that's leaving the surface of the sun and that's being replenished down in the core of the sun by the interior, by the fusion that's happening deep in the core. So there's a flow of energy from the inside all the way out, and that's a thermal equilibrium. But of course it ends, right? Because the fuel eventually runs out. But for now, it's in thermal equilibrium. How did it get this way? So there are two things that must occur. First, it must form some dense protostar, and then after that, you establish thermal equilibrium, and then that's the pre-main sequence phase. So there's really two sets. You got to do one, then the other. Hydrostatic equilibrium means it's in balance, but then deep in the core, there must be something that generates the heat, and that's the pre-main sequence phase. When are stars actually born? So we can find out that by looking around the Milky Way. And the space between the stars is called the interstellar medium, and it's filled with gas and dust, and the dust that we see that fills the interstellar medium is the size of a roughly cigarette smoke. And cigarette smoke is only a few microns in size, but if you take a cigarette and puff it into a white light in a darkened room, you see a blue smoke. And that's because particulates that are the size of the cigarette smoke preferentially reflect and scatter blue light. It's not because the particles are blue, it's because they scatter blue light more easily than they scatter red light. So the dust in the light looks blue. Now, most of the volume of the Milky Way is filled with this enormous, thin diffuse atomic hydrogen gas. It can be cold on the order of a couple hundred Kelvin, but it can also be very hot and just hot enough to glow. Embedded within all of this volume, though, are these enormous clouds that are very dense, that contain molecular hydrogen, and they're cold areas. And this is where young stars form. And all young stars are found in these dense gas-rich regions, and they're found next to these clumpy areas where there's big clouds. So we should find stars forming next to where the stuff is that they're formed from. And these things are called giant molecular clouds. They're interstellar clouds, mostly of molecular hydrogen gas and then filled with the dust between them as well. They take up about 1% of the volume of the Milky Way, but they take up more than half the mass. And half the mass of the Milky Way isn't just stars, it's this gaseous clouds and clouds of gas and dust. And they make up an enormous amount. So the stars you see in the sky don't make up the dominant amount of mass. And we're talking inside the sun's orbit, it's about half the mass of the Milky Way. And the sizes of these clumpy things, these clouds, are between 5 and 200 parsecs, so they're quite enormous, much larger than the individual stars that make them up, or that form out of them. And the masses of these huge clouds can be between 1,000 and up to 10 million times the mass of the sun. They tend to be much colder, and almost a few dozen degrees above absolute zero, but the clouds that permeate the Milky Way, they have very low densities between about 100 and 1,000 molecules or particles per cubic centimeter. And the core, though, when we find core like cloud cores, they're much more dense, between 100,000 and a million molecules or atoms per cubic centimeter. Now, if we compare that to nearby the sun, the interstellar medium near the sun, that's about one, which it is only about 1 molecule per particle or cubic centimeter near the sun. So clouds are much more dense than near the sun, and the molecular cores are even more dense. By comparison, if you go and look at the vacuums made in laboratories, there are many, many tens of billions, if not trillions, of molecules per cubic centimeter. So even though the objects that we see that we call giant molecular clouds, we can't see through them, but that's not because they're made of solid stuff. They're better vacuums than we can make in any laboratory on Earth. It's just that they're so incredibly vast that they scatter all the light and absorb the light that passes through them. And it's interesting because something that starts off as 200 parsecs in size eventually ends up a few hundred thousand kilometers across. So it's an enormous drop in size scale. So you have to collapse the cloud. So let's see what balances it against that collapse. And the stuff that's inside a giant molecular cloud is either neutral hydrogen, H1, which is just an atomic hydrogen in the upper left. That's a proton orbited by a little electron. And now if it's hot, though, it'll be an H2 region. That reads HII. It was Roman numeral 2, and now it is an ionized proton with an ionized electron, and they're zipping around. It's electrically neutral because there's an equal number of each, but they're free from each other, and that must mean they are close to some hot ionizing source. Now, if it's truly cold, the atomic hydrogen will bind together and dense. If it's cold and dense, it'll bind together to form molecular hydrogen, where the two protons then share an electron and form a molecular bond. And in such environments, we also find molecular carbon monoxide, both of carbon-13 and carbon-12, where there are different isotopes of carbon. And then we also find ammonia and methane and such things like that with quadratomic molecules such as these. And so these are the kind of molecules you find, and they're very small molecules, but these are the kinds of molecules that scatter blue light in just the same way that particles do. And there's also dust particles, which would be made up of little clumps of these molecules. Not very big, but just big enough to be about the same size as cigarette smoke. Now, there are 3 phases to the interstellar medium, and we're not talking about all of them this time. Before, we talked about the hot ionized medium, which is 1 million to 10 million Kelvin, and those are galactic clouds that rise well above the plane of the Milky Way. But if we look at the cooler areas, the warm and neutral ionized media, which can be either ionized hydrogen or a neutral hydrogen, between 6,000 and 12,000 Kelvin. It's mostly the upper right-hand one. These arrows are a little bit dodgy with respect to that, so we're looking, the top one is definitively ionized and it goes way above and below. But the warm and neutral one is between 6,000 and 12,000 Kelvin, so we see some of the effect of the upper right-hand image. And the densities then are only about a 1/100th of a particle per cubic centimeter. And it's even more thin on the much hotter areas. But now we're talking about the cold stuff, which is more like the bottom image and the right-hand image, which are evident only from the molecular hydrogen from the Milky Way, that's what the MW stands for, the Milky Way emission from 21 centimeter radiation, as well as carbon monoxide emission, which will be cloudy and clumpy like we see below, where the densities are between 100 and thousands of particles per cubic centimeter, and the temperatures are really, really low. And this is where stars are forming. Not the hot stuff, but the really, really cold, dense stuff. And so the molecular cloud, such as the Eagle Nebula here we see, which is a prominent molecular cloud that's part of the Eagle Nebula. Now these things are self-gravitating. It doesn't matter that they're a couple light years long like these are, but they contain, even though they are diffuse, they are self-gravitating. And they contain mostly hydrogen. Even these objects that you're looking at mostly are hydrogen, but then there's these dust grains, and the dust grains are that absorb much of the ultra-infrared light. They of course, they occupy these giant molecular clouds are between about 30 or 50, or about half of the mass of the entire Milky Way galaxy. But they only occupy about 1% of the volume. So these are tight little things, but they're, by little we mean a few hundred parsecs or so, between 5 and 200 parsecs across. But then when you get to the cores, like you see in these pillars, the pillars of creation in this Hubble image, this is where stars form. So how do stars form? Because you got to take a cloud and you got to collapse it. So there's some things that keep it from collapsing. And so we have this diagram on the upper right of kind of what a cloud might look like. So you got this ball of hydrogen on the upper right, and then in an empty space. So if you have a ball of hydrogen, the only thing that's going to be supporting it, it might have some internal pressure from just the motion of the gas inside it to try to push it out, but then it'll be self-gravitating to try to pull itself together. So the potential energy from the gravitational pull and will be balanced by the kinetic energy of the motion of the gas inside it. So we can then take the kinetic energy and we can add another term that pushes from the outside. Maybe there's a shock wave that comes along and whacks it. Or maybe two of these clouds smack together, or the winds collide. And so now you've got extra kinetic energy from external pressure that might try to push it together. And so now that's what the red around the blue cloud seems, is like something's pushing it, maybe something comes and kicks it, and then it starts the process. This then creates turbulence inside of there, and the turbulence then balances it against the pressure. So that's the next thing, is that you whack a gas and it becomes turbulent. In the same sense that when you take a little bit of milk and pour it into coffee, it doesn't really show those turbulent little flows until you stir the coffee. So those are the turbulent little swirls, and that tends to balance out the pressure. So now you've got motion, additional bulk motion, that then stirs the cloud. This adds more thermal energy and also contains kinetic energy, but that still attempts to balance the potential energy from it gravitating together. And then you've got an additional energy that tries to either push it or pull it across, and that motion may create a weak magnetic field that then adds together, and all of these things balance out, hopefully, in the cloud, the turbulent motions with an ionized gas, or lightly ionized gas, because now it's warm or maybe hot, has a tiny magnetic field, but that's just enough to actually cause additional motions throughout the cloud that can dissipate it. And so if you have some sort of a magnetic field associated with it, and there's turbulence, there's kinetic energy from turbulence, there's kinetic energy from heat, there's kinetic energy from heat, meaning the motion inside the cloud inherently, and there's kinetic energy that comes from being pushed upon, and it's all trying to be pulled together by gravity, and the magnetic field is trying to pull it together too. And if it's in some sort of equilibrium, then you've got some sort of crazy cloud, but it's a wibbly, wobbly, glibbly, globbly, ugly mess. And that's what all of them tend to look like. And they have this dense sort of core that's being pushed from the outside, and there's all sorts of turbulence, and then we see like the Eagle Nebula. So this is a schematic of what's going on with all this energy supplied by weak magnetic fields. Anyway, so a giant molecular cloud is held up by its own gravity, by internal pressure, and that pressure comes from internal heat. It also comes from pressure from magnetic fields, so that's the thing that holds it up. And if the gravity becomes larger than that internal pressure, if somehow the gravitational field becomes larger, and how that happens is because you got to push on it. And if it happens from clouds colliding, maybe two clouds collide, maybe there's a supernova that causes a shock that pushes it together, maybe it passes through a more dense region of the Milky Way by passing through a spiral arm where there's more stuff in the general vicinity, and then you get some collapse of the giant molecular cloud to form more stars. So then when it falls apart, these giant molecular clouds form clumps. And the clumps can be really small, down to 1/10 of a parsec, which is still really enormous, right? 1/10 of a parsec is about 3 3/10 of a 30% of a light year. So the parsecs are about 3 light years. So this would be about like 0.3 light years. It's a pretty big thing. So these masses of these clumps that are a few solar masses. And the high density clumps are then even more unstable, and now they can start to collapse. And this results in if you have some sort of shock that comes along, that causes them to fragment into little cores, and those cores have cores, and those cores have cores, and so on and so on. And we observe them first, where this might occur, by the density of the radiation that we see from 21 centimeter radiation. And again, 21 centimeter radiation happens because you have atomic hydrogen, and the electron and proton have their spins aligned and in a parallel, and then the electron, just in general or just because, and maybe there's just a light disturbance, it has just a little bit more energy than if they're spinning opposite. And so if they're spinning parallel, they have a little bit more energy, and then it can radiate a photon by flipping its spin. The electron flips its spin, and it radiates a little bit of radio light. And so this is where, if we see a lot of this 21 centimeter radiation coming from a place, then there's a lot of the cold gas there. If we don't see much of it, there's not much. So we first look for the cold molecular gas from the 21 centimeter radiation, which is this process. And this is where we see the cold molecular gas. It's confined to the plane of the Milky Way in this tight band across the Milky Way. And this is an all-sky survey of 21 centimeter radiation centered on the galactic plane. And so that's what the plane across the middle is, which is the plane of the Milky Way. And as we look at the plane of the Milky Way, the center of the Milky Way is at the center of the image, and 90 degrees up from the Milky Way, looking straight out of the Milky Way from our perspective, is the top of the image, and 90 degrees south from the Milky Way is the bottom of the image. So this is an all-sky map of the Milky Way projected onto a disk. So we can see some looping, arching clouds, but mostly it's confined to the Milky Way. And then if we look specifically at the radiation of carbon monoxide, which is a tracer element for molecular hydrogen, even the colder spots, we find that this is particularly clumpy, but with a significant fraction of it coming towards the center of the Milky Way. And if we look away from the center of the Milky Way, it gets diffuse and lumpy. So the vast majority of the gas and dust of the Milky Way is interior to the sun's orbit around the Milky Way. And we see that this image was taken by the European Space Agency's Planck Space Telescope as they were looking for the cosmic microwave background. And so this is something they had to take into account to look for the great background. And so those wavy sort of structures, that's because of the artifacts from reducing this image. All right, so what do these globs look like? One of them are called Bok Globules, and that's named after Bart Bok, who was a friend of mine when I was a child. And these are places where there's mostly molecular hydrogen, there's carbon monoxide, there's a lot of helium, of course, because we forget about that because it's always in the form of a gas. So there's gaseous hydrogen, gaseous helium, and that's almost everything. And then there's maybe even silicates, which are carbonaceous things. And these silicate dusts would be what we're talking about with the cigarette type smokes. And so carbon is an incredibly common element in the cosmos, so we would expect that to be there too. So when we look at these objects, they're about a fraction of a light year across, and they can be up to 2 to 50 solar masses. So each one of these globules could, in theory, form a star at some point because they're dense enough that they are cores that could form stars inside of them if they collapse further, such as Barnard 68. This is another molecular cloud. It's about 500 light years away, and it's all isolated, unlike the Bok Globule that we saw before that was in front of an Emission Nebula, a pink Emission Nebula, illuminated by bright stars. But Barnard 68 absorbs the light from the stars behind it, and we see the effective interstellar reddening in the stars on the periphery of the cloud. But the interior of the cloud is so dense that, well, by so dense, we mean it's got about 1 million particles per cubic centimeter, which is really which is an incredible vacuum compared to what we find on Earth, that this cloud is in the process of collapsing, and it will either collapse down to make new stars, or it will dissipate over time, depending on how much kinetic energy and how much, whether it's collapsing down or if it has enough energy to resist against the force of gravity, like the diagram we talked about a bit ago. But such molecular clouds like these are even darker. So this is the Circinus Molecular Cloud, and this is another Space Telescope image What we're looking at is this particular thing is dark nebula in the background that looks like it has wings. Is an enormous structure that is almost 250,000 times the mass of the sun, filled with huge numbers of things, and there's even young stars forming. And some of the young stars have become so bright and so intense that they've actually punched a hole and eaten away or dissolved or evaporated the gas around them. And so now we see into the place where the star has formed. And there's lots of different regions inside of here. The two prominent regions, and they're each about 5,000 solar masses, so they could, in theory, make 5,000 masses of the sun. Now we can also see the effect of the cloud has got this snake-like shape, but it also has a wispy outer area. If we look on the right-hand side of the image, we see that the view is mostly unobstructed, but if we look in the top center, we see the effect of interstellar reddening because of the cloud that is diffuse above the snake-like structure. So the most dense area is at the bottom, the cloud is above. So something caused this to collapse so that it would form stars. And it almost looks like a shock wave, right? So it's like we have the nice under-dense cloud at the top right of the image, and then the middle of the image is where we see a lot of the high-density region. But then the lower density region is to say at the bottom of the image and off to the right. So it's as though something moved in from the lower right, smashed into it, formed this molecular cloud, and then it started collapsing to make stars. So some shock wave came along. Maybe there was a big supernova that happened out of the field, and that shock wave then impacted this cloud that used to be as diffuse as what we see in the upper right, and then that all bunched together to form this one big cloud and then form more stars. And finally, we look at we see a part of an enormous molecular cloud that's so big it almost takes up an entire constellation. That's why we call it the Taurus Molecular Cloud. It's so big it's almost as large as the entire constellation. And this can only be seen, the red glow comes from submillimeter wavelengths, which is 0.1 millimeters or 0.01 millimeter wavelength roughly. And this filament is approximately 10 light years across. And inside those bright spots inside it are where newborn stars are forming inside this long, long, long filament. And the background image is composed from the Digital Sky Survey, just to put it on top, because submillimeter wavelengths don't show stars. So you put a visible light image on top of it. That's why there's two different resolutions. You'll see sharp resolution for the stars, and you'll see kind of low resolution clumpiness in the cloud. And this was taken by the European Southern Observatory at the Apex telescope. And finally, we'll finish off with a Spitzer Space Telescope image from Jet Propulsion Laboratories. We're showing the Serpent star cluster smack in the middle, and then there's a tiny filamentary molecular cloud that goes left and right through it. And the molecular cloud is, of course, the dark region that formed the star cluster, and now the star cluster has burst out and has used up much of the cloud to make the stars. Still, we're surrounded by the pinkish glow of hydrogen, but that pinkish glow is because now the hydrogen is hot or warm because of the baby stars that are extraordinarily hot, that illuminate, that not just illuminate means shine light on. Actually, they do shine the light on it, but then the atomic hydrogen takes the ultraviolet light from all of these baby stars, and the electrons in the hydrogen jump out of their orbits and are ionized out to distances of light years. So the reason this is a pinkish glow is because the hydrogen is ionized out to distances of light years. So you don't want to be next to these bright stars, because if you're next to these bright stars, you'd be getting a heck of a sunburn, as your skin would be ionized. That's what that means. That's what that pink glow means, and that pink glow of ionized hydrogen. But the dense clouds that are in the background, those things are the remnants of the big cloud that used to be there, that the baby stars then formed out of, and they'll probably prevent the formation of more stars because, well, that cloud's getting used up and it'll probably be dispersed by the bright energy of the young stars, which will then evaporate the cloud itself. So these clouds are very temporary structures. They flow in, they flow out. Once they start to form stars, that's pretty much the end of their life, as they do, and so then they either get dispersed or they form more stars. And in general, there's a very thin diffuse gas to most of the Milky Way, and then it collapses, and it might have some turbulence that then brings the cloud together. And that's the story of the beginnings of the star's life. Now, next time we'll talk about protostars and see how stars are born. We'll see you soon.